Welcome back to our discussion on electromagnetic rays and their relationship with light. We took a look at the idea of the index of refraction in the last lecture. The index of refraction is a unitless quantity that is defined to be the factor by which the speed of light diminishes when light travels through a material. So, for instance, light is slower when it travels through glass than it is when it travels through the atmosphere, and it's slower in the atmosphere than it is in vacuum. In fact, light in vacuum is as fast as it gets, and that is the quantity denoted by lowercase c, the speed of light in vacuum. And our formal expression to determine the speed of light in a material is that it's equal to c, the speed of light in vacuum, divided by n, the index of refraction. Now, if light crosses a boundary where the index of refraction is one value to a region where the index of refraction is a different value, the speed is going to have to change. And considering that the speed of light is equal to frequency times wavelength, if the speed of light changes, then either the frequency changes, the wavelength changes, or both change. Let's see if we can apply a little logic to see which one of these or both of these is going to change. Now, frequency is the rate at which peaks of light enter the boundary. Now, if the frequency increases, we're saying that maybe 5 peaks per second enter the boundary and 7 peaks per second leave it. Well, where are those other peaks coming from? That doesn't make any sense. This is not happening. And if the frequency decreases, it's like having 7 peaks per second enter the boundary and only 5 peaks per second leave the boundary. In principle, maybe this happens, but that would result in an energy buildup at the boundary. And at some point in time, the boundary would probably melt or something from all the energy. We don't observe that. This does not happen. So the frequency does not change when light crosses a boundary. So if the frequency doesn't change, but the speed does, we're left with saying that the wavelength changes. And we've done all sorts of experiments, and we have found that it does indeed decrease with n. Let's just do a quick and dirty example. You can look up diamond that has an index of refraction of 2.42. And suppose we want the speed of light in diamond, and suppose we want the wavelength of light in diamond when the vacuum wavelength is 543 nanometers. These are two quick calculations. To find the speed of light in the material, you take the speed of light in vacuum and divide by the index of refraction. 3 times 10 to the 8 divided by 2.42 equals 1.24 times 10 to the 8 meters per second. The wavelength is treated the same way. The wavelength in diamond is equal to the wavelength in vacuum divided by the index of refraction. 543 nanometers divided by 2.42 equals 224 nanometers. Now, despite the fact that the wavelength has changed, keep in mind the frequency doesn't. And as a consequence, if you've ever been in a swimming pool and been underwater and opening your eyes underwater, the colors of things seen through water basically remain the same. And in part that is due to the fact that your eyes are not responding to the wavelength of light, they're responding to the frequency of light. The rate at which light is entering is going to affect the color that you see. And since the rate doesn't change when it travels through a medium, well, the eye is not going to see any different color. Of course, it gets a little more complicated. We see an ordinary example of this being more complicated in a rainbow. A rainbow is an example of a phenomenon known as dispersion. Dispersion plays into the fact that the index of refraction isn't the same for all materials. And in fact, materials don't even necessarily transmit all wavelengths and frequencies equally. Some wavelengths, some frequencies in particular, are absorbed. So we see an example, this painting on the left, where half of the painting was covered with a glass that was opaque to ultraviolet light, and the other side, the right side, was covered with a glass that would let ultraviolet light through. And the side that didn't let ultraviolet light through is less faded. On the right-hand side, we see a graph, something on the vertical axis called transmittance, and on the horizontal axis, wavelength. The horizontal axis from 400 to 750 nanometers, that's the range of visible light. And you can see that the transmittance, the amount of light that gets through, drops off precipitously below about 420 nanometers. And less than 400 nanometers, no light is getting through. Now, it turns out that that's the region of ultraviolet light, less than 400 nanometers. So ultraviolet light doesn't get through, visible light does, and so we can see the painting, but the ultraviolet light doesn't cause it to fade over time. Now, these two phenomena, a rainbow and this special glass, are related because different materials will absorb light of different wavelengths and different frequencies. And if the wavelength or frequency is not exactly at the optimum wavelength or frequency, well, there's still a good chance it's going to get absorbed. You have to be noticeably far from one of these absorbing wavelengths for there to be no absorption whatsoever. And the fact that the absorption changes with wavelength, some wavelengths being more likely to be absorbed than others, that also means that the index of refraction will change depending upon wavelength and hence depending upon frequency. Now, why is it that the different wavelengths are absorbed and others aren't? And it really depends upon quantum mechanical effects. The atoms all have different energies that are more particularly interesting to them than others. Not all energies are the same. And an energy is associated with a frequency. And if it has just the right energy, it must have just the right frequency to make it much more likely to be absorbed. If it's not exactly at that frequency, well, there's still a good chance it will be absorbed, but the further away it gets from that frequency, the less likely it is. That frequency at which it gets absorbed is called a resonant frequency. And, of course, it's not so cut and dried as that. There's typically a narrow range of resonant frequencies rather than a finite resonant frequency. So you might get a broader looking resonant spectrum than just focused on one frequency. So on the screen you can see a graph with a slightly wider spectrum in which the light is particularly favored. Now, you don't have to know any equations like that equation on the previous slide. That's 1 over F minus F naught squared. Don't sweat over it. This is just giving you some conceptual understanding of what's going on. Different atoms are made up, materials are made up of atoms and molecules. Different atoms and molecules like the taste of different energies of incoming light. Light that doesn't have that right energy, it just lets on through, but light that does have that right energy, it's more likely to absorb it. This is the absorbance pattern of water. So where it is high is where the light is most likely to be absorbed. And if you look at it, you'll see that water does a really good job of absorbing wavelengths less than visible light, which is represented by the thin rainbow line, and it's also pretty good at absorbing wavelengths longer than visible light. Water is pretty bad at absorbing visible light. Well, you probably noticed that you can see underwater at a reasonable distance. Not as much as in air, but you can still do pretty well. But there's another thing to notice. The absorbance rises for red The absorbance for red is a little bit better than the absorbance for blue or green. And you've probably encountered this phenomenon before. When sunlight reflects off of water, the red light is a little bit more likely to get absorbed, and the light that reflects off of the surface is a little bit more blue heavy. So water appears slightly bluish because the red light falling on it is more likely to be absorbed, just slightly more likely to be absorbed. Now that rainbow pattern that I called the visible light, you can see where it falls in the scale of things. Visible light is an extremely narrow band of all the kinds of light that there actually are. There are far more kinds of light than visible light. We only learned about this in the late 19th century, of the existence of ultraviolet light or infrared light. It was quite an astonishing discovery that you can look in other parts of the electromagnetic spectrum. Visible light, of course, you have the canonical colors, red, orange, yellow, green, blue, and violet. Some people will say indigo is in between blue and violet, but you still have these colors. And you can also see the wavelengths associated with them. Red light goes out to about 700 nanometers, orange is around 625, yellow is around 550, green is around 520. You get blue, that's around 470, and you can get the violet, that's close to 400. So as the wavelength gets longer, the color goes towards red. Short wavelengths, that's blue or violet. Long wavelengths, that's orange and red. And similarly, the frequencies. Slightly lower frequencies, that's the red and the orange. Slightly higher frequencies, that's the blue and the violet. But look at all those other kinds of light. And notice that this scales, whether you're looking at the wavelength in meters on the upper scale or the frequencies in hertz on the bottom scale, it's a logarithmic scale. This is not linear. So each tick mark differs in magnitude by a factor of 10 from the adjacent tick mark. And these tick marks are pretty close together. So you can see that visible light is a very tiny region, 400 nanometers to about 700 nanometers. Let's look at these other kinds of light. And first off, visible light is certainly the most obvious. Now, why is it the most obvious? Because that's the kind of light the sun is most likely to emit. The sun does emit all different kinds of light, but it's visible light that is predominant. And seeing as how we evolved on this planet with this sun shining down on us, it was this range of wavelengths that would be most optimum for us to be able to see, at least in general. So we evolved to see this range of colors because that's what the sun most likely emits. You might be able to make some guesses as to planets orbiting stars with slightly different colors and a slightly different output spectrum, and maybe they see colors that we don't. Our eye also evolved somewhat discreetly in the sense that there are 3 different kinds of color-sensing cells in the retina. The color-sensing cells in the retina are known as cones. They're to be distinguished from the simple light-sensing cells that are called rods. Rods typically just say whether or not there is light. Cones see whether there's light, but can also tell you what color it is. Rods tend to be more sensitive to light, so when it's really dark and there's very little light, you're more likely relying on your rods in your retina than the cones. The cones in our retina are optimized to some very particular wavelengths, as seen on the screen. There are these blue cones that are optimized for 420 nanometers, green cones that are optimized for 525 nanometers, and reddish, orangish cones that are optimized for 545 nanometers. but you can see that they spread throughout the entire spectrum. But then these light cones are not in equal quantities. Now, each individual has different proportions of colors, so some people might see the blue end of the spectrum better than other people. Some people might see the red end of the spectrum better than other people. But on average, there are significantly more red-sensing cones than there are green-sensing cones, and more green than there are blue-sensing cones. I don't know if any of you are into photography with film, but you might have heard of dark rooms and maybe seen it in old movies or something. And in the dark rooms, they have these lights that emit red. They tend to be very faint light bulbs, but they tend to also be in the red part of the spectrum. Our eyes are more sensitive to the red part of the spectrum on average. So a dimmer source of light can still be seen if that source of light is predominantly red. And so by having a dimmer source of light, you're less likely to expose that film, and blah, blah, blah. So while we are optimized to see the visible parts of the spectrum, there are certainly other parts of the electromagnetic spectrum. And when we start looking at wavelengths longer than visible light, beyond red, we first encounter infrared light. Infrared light is often thought of as heat vision. On the left and on the right is an image of the geyser Old Faithful, and you can see how it looks like in visible light on the left, and you can see how it looks in infrared light on the right. Now, the color coding on the right is completely artificial. Exactly how it would appear in colors, well, we would have to ask somebody who has cones in their eyes that could sense infrared light, and we don't know anybody like that. So this is an artificial coloring, but it gives you some idea of how it would look compared to the visible part of the spectrum. We can also look at a person wearing sunglasses, and we can also see the appearance of a hurricane in infrared cameras. And again, we also can look at more mundane sorts of things. These are astronomical observatories atop Hawaii's mountain Mauna Kea. And again, this is shown in infrared. Again, the colors, all these colors are false colors. They were put in by someone who just likes the way they look. They were programmed that way. Who knows what those colors would actually appear like to someone actually optimized to see infrared light naturally. If we go to wavelengths longer than infrared light, we then encounter microwaves. And yes, these are exactly the microwaves in the microwave oven, but they are also used in short-range communication devices. For instance, a TV remote or a cell phone. And I have to admit, I miss flip phones. They look so cool. So I have a flip phone image here. Deal with it. We can take a look at the sky in microwave light. If we somehow had the capability of naturally seeing microwave light, we would see some parts of the sky brighter than other parts. Examining the night sky in microwaves is one of the habits of astronomers, and they've been able to gain some interesting information about, of all things, the Big Bang and the origin of the universe. Microwaves are also effective in microwave ovens and wet puppies because water is a good absorber of microwaves. If we go back to that slide of the absorbance of water, you can see that in the microwave range that water has some relatively high absorbance for microwaves. Water is very likely to absorb microwaves. And what that means is that the water in food, and most foods have water in them, the water is going to absorb that energy and in the process heat up and the water molecules will be bumping around and what have you, and they'll be heating up the environment around them. So you get your food hot because the water in there is going to heat up and warm up the adjacent food around it. There are other molecules that are good at absorbing microwaves, but water is arguably the most significant contribution. Water, because of its ability to absorb infrared and microwaves, is also a greenhouse gas. So we get all sorts of light coming in from the sun, and the light goes through the atmosphere. There's water vapor in the atmosphere, and some of that energy is absorbed. And then the light falling on the surface heats up the surface, and the surface wants to emit infrared light, but the infrared light is bouncing around in the atmosphere with all of these water molecules. And the water molecules just eat that energy up. And all they do is they hang around and gain energy, and the temperature of the atmosphere goes up. Now bear in mind, without the greenhouse effect, the surface of the Earth would be uninhabitable. So the greenhouse effect in general is a good thing, but the concern is that there can be too much of a good thing, and that's why we have to worry about greenhouse gases like methane and carbon dioxide. For even longer wavelengths than microwaves, we have radio waves or TV waves. You can see on the right-hand side these telescopes, these radio telescopes are optimized to see radio waves, and notice the size of them compared to an ordinary person. These are gigantic. If you wanted to naturally see radio waves, you would have to evolve eyes about as big as a radio telescope. So it's just not very convenient for the lumping around the surface of the planet and having eyes as gigantic as that. So we did not evolve to see radio waves, but they still exist. If you were to look up at the night sky in radio waves, and if you could imagine it looking like a starry night, you would see the image on the left. You see lots of spots there that look like stars, but then you also see these splotches. Those splotches tend to be the remnants of exploded stars. And those small lights that look like stars, those are actually galaxies. Those are very distant galaxies. So it looks the same in many ways, but there are some profound differences. Now let's take a look at wavelengths shorter than visible light. And the first type of light we encounter with such wavelengths is ultraviolet light. We know ultraviolet light as what we use to get suntans, or if you get too much, skin cancer. On the right-hand side, we see what the sun would look like in ultraviolet light. Again, false colored, but you can get an idea that there are some interesting differences. It doesn't look nearly as uniform. While we can't see in the ultraviolet part of the spectrum, some insects can. Some insects can very easily see in the ultraviolet part of the spectrum. Now, why is that? Well, they evolved that way. Take a look at the flowers on the left in regular light, and then these same flowers on the right in ultraviolet light, and you'll see that these flowers on the right are a much more interesting target when it comes towards bees gathering nectar. Once upon a time, we had a hole in the ozone. Ozone is an unstable variation of an oxygen molecule. Most oxygen molecules are O2. Ozone is an unstable O3 molecule. But just because it's unstable doesn't mean that it doesn't exist. There is a small amount of ozone in the atmosphere, particularly in the upper atmosphere. Well, once upon a time, we were using a type of refrigerant called chlorofluorocarbons. And then these chlorofluorocarbons would escape into the atmosphere, and one chlorofluorocarbon was capable of negating up to 100,000 ozone molecules. And so the accumulation of these CFC molecules was causing a depletion of ozone in the atmosphere. And the depletion was fairly significant over the southern part of South America and in Antarctica. With the discovery that CFCs were causing this, there was an international effort to decrease the use of CFCs. This international effort succeeded. And with the decline of CFCs in the atmosphere, the ozone hole has been shrinking and shrinking and shrinking. And at the last time I checked, it's very nearly back to being no hole at all. So it is possible for the international community to work together. Go figure. Ultraviolet light comes in three brands: UVA, not after the university, UVB, and UVC. UVA tend to be the longest wavelengths and are the least damaging. But UVB and UVC have shorter wavelengths, they have higher energies, they can cause more damage, and if that ozone hole had spread, we would be seeing more UVB and UVC rays reaching the surface, and there would be more incidences of skin cancer. If we go to even shorter wavelengths than ultraviolet light, we encounter X-rays. X-rays weren't discovered until 1895, when a German scientist by the name of Wilhelm Röntgen kind of inadvertently discovered it. He realized almost immediately the value of these rays. He took this X-ray image of his wife's hand. As you can see in the image, you can see that she was wearing a ring at the time. And he wound up winning the very first Nobel Prize in Physics in 1901. The discovery of X-rays was a blessing for the doctors. They now could examine the bone structure of people without actually cutting them open. And initially, they would set up these stages at universities to almost conduct a show, and they would hire some poor sap off the street. And they would expose this poor sap to an X-ray emitter that was then projecting what was happening onto a phosphorescent screen. And on the screen, all of the doctors in the audience could see the patient lift their arms, lift their legs, twist around on their hips, flex their hands, make a fist. But unfortunately, these poor saps were just getting exposed to X-rays and getting exposed for minutes at a time, and they were getting these serious burns. If you've ever been to the dentist to get an X-ray or some other place to get an X-ray, one of the things they do is they put a heavy bib over you, over the parts that aren't getting X-rays. That heavy bib is lined with lead. Lead blocks X-rays. You want to limit the amount of exposure to X-rays over the course of your life, because they can cause burns and they can cause cancer, just like ultraviolet light does. In the atmosphere, X-rays don't tend to travel very far. If you have a ground-based X-ray telescope and you turn it to the night sky, you're not going to see anything, because all of the X-rays that are bombarding the Earth are getting absorbed by the atmosphere. It wasn't until the late 1970s when we started sending up orbiting spacecraft that were capable of detecting X-rays that we could start taking a look at the universe in X-ray light. On the screen, you can see an X-ray image of a supernova remnant. You can see the explosion still expanding outwards. And at the very center, you see a white spot, a tiny white spot above the arrow. That is a neutron star. The neutron star is the remnant of the star that blew up. It's the remaining core of that star. So that's something that you can see in X-ray that would be much more challenging to see in visible light. That little neutron star, which puts out gargantuan amounts of X-rays for its size, is basically swamped by the light of the surrounding cloud of explosive debris. Even shorter wavelengths, and therefore even higher frequencies, are gamma rays. Now, gamma rays are some bad juju. You don't want to mess with them. We saw that ultraviolet rays could cause skin cancer, X-rays could cause burns and cancer, and gamma rays can very definitely cause cancer. You don't mess with gamma rays. What you see in the picture on the upper right are two pellets of plutonium. Plutonium is one of the most egregious emitters of X-rays around. It's highly dangerous. On the left-hand side, you see an image of the night sky in gamma rays, and the bright band is basically stars in the Milky Way galaxy. And then, of course, on the lower right, you see a once-in-a-million years fluke of what can happen with gamma ray exposure. The image on the left was taken by the Hubble Space Telescope, and again, it's false colors, but what they are is an X-ray image of jets of gas being emitted from the center of a galaxy. We have an entire galaxy there, and there's a huge jet of light being emitted in each direction. The speculation, the hypothesis, all but confirmed, is that there is a gigantic black hole at the center of this galaxy, and that gigantic black hole is devouring stars that come too close. And in the process of devouring the stars, there's this ejection of this focused ejection of energy in opposing directions. Okay, that's enough for now. I hope it was fun. Take care. Bye-bye.